Will be presenting work done by himself, Yang Zhang, and Chris Harrison on advancing hand gesture recognition with high-resolution electrical impedance tomography.
Great. Thank you so much for the introduction. So tomography is a general technique of using penetrating signals to image a solid object from outside. It comes in a lot of different shapes and sizes. There are tomographic techniques for geological surveying, for fault detection in manufacturing, for archaeology, for oceanography, and for many other fields of study. For our purposes today, we're interested in tomographical techniques for imaging the human body, of which there are a few common ones. All of the tomographic techniques for imaging humans basically rely on the fact that different tissues in the body, such as bone, muscle, and skin, respond differently to certain penetrating signals. When we map out the distribution of these different responses, a picture of the internal structure can be reconstructed. So let's go through some different kinds here. Positron emission tomography, or PET scans, use gamma rays to image the human body. And that's very accurate. Gamma rays are very small, but it's not suitable for daily use because it's irradiation. Computed tomography, or CT scans, similarly use lower energy X-rays to achieve the same result, building a 3D model of the body using a bunch of 2D slices. Magnetic resonance imagery, or MRIs, use powerful magnetic fields to image the body. And finally, electrical impedance tomography, or EIT, use electrical currents to measure the profile of the body. And here you can see the pictures basically for three of the machines, or all of the machines for each approach. Now, for the first three, you can see that the machines are really big, very expensive, and probably pretty hard to miniaturize. They use fairly high energies involved. EIT, on the other hand, has much simpler requirements. Instead of radiation or strong electromagnets, EIT requires only electrical current. That's very easy to generate and sense. And furthermore, EIT can operate with a very low level of current and making it very safe. So with EIT, you stick an array of electrodes around the object to be measured. Here, we're sticking electrodes around a baby's chest. Current passes between those electrodes, and measurements are taken to determine the internal impedance distribution, from which you can then infer the internal structure. Here, we're measuring the baby's lung cavity because the lung has a higher impedance than that of the surrounding tissue. This allows us to measure respiration in this case. Last year at UIST, we introduced Tomo, the first application of EIT to human-computer interaction. Tomo consisted of an armband with an attached sensor board, a drastically miniaturized version of a commercial medical EIT system. It's also a heck of a lot cheaper, from hundreds of thousands of dollars down to a $50 sensor board. Here you can see Yang wearing the Tomo armband, and on the left you can see the image reconstruction on the screen, showing basically the cross-section of his wrist. Tomo had 8 electrodes and a fairly simple sensing approach. It was our first foray into EIT, and for an early prototype, this system worked pretty well. We were even able to do simple gesture recognition, which we demonstrated at UIST. In the intervening year, however, we've been working on significant improvements to Tomo, drawing on decades of medical literature in EIT and our own experiments on the topic. We wanted to know what kind of factors we had to improve in order to improve the system accuracy and the ability to sense different gestures. Specifically, we experimented with the sensing modality and the number of electrodes, and I'll detail that in a second. In order to actually do these experiments, we had to build a completely new prototype system. I will detail all those explorations we did and the studies that we did to compare and evaluate those different approaches. We believe that with these explorations in place, we've pushed the boundary on the use of EIT and HCI, and we're really excited to see what people do next with this technique. So first of all, we explored different sensing techniques. Tomo used an EIT sensing mode known as two-pole sensing. In two-pole sensing, 2 electrodes are used to make a single measurement. So here we can see a cross-sectional view of a human arm, to which we attach 2 electrodes. We create a 300 microamp constant current AC signal running at 40 kilohertz between those electrodes. The voltage of that signal is going to depend on the impedance distribution along the electrical path between those 2 electrodes. And so if we measure basically the voltage difference between those 2 electrodes, we can then infer the impedance along that electrical path, and we use the root mean square measurement in our system to smooth out those voltage fluctuations and actually perform that calculation. If we were then repeat that process with every single pair of electrodes, we'll basically get pairwise measurements covering a large number of different electrical paths. If we then apply image reconstruction algorithms specialized for the EIT problem, we can then build a profile of the impedance distribution within the human body. Now, this two-pole sensing approach is conceptually very simple and simple to implement, but the major drawback is that it's very sensitive to the impedance at the electrode itself, because that electrode is also part of that electrical path that's being both generated and measured. If that electrode has a different impedance, for example, if it's not securely attached, or if the skin happens to be wet with sweat, then the measurements will change significantly, and that will adversely affect accuracy. So the alternative sensing approach is four-pole sensing. In four-pole sensing, the signal emitting pair and the sensor pair are distinct. So here, for example, we have the two electrodes 1 and 2 emitting a current shown as I, and all of the other pairs, 3, 4, 4, 5, 5, 6, etc., are used as basically current voltage measurement pairs, denoted in V. So it's called four-pole because we use 4 electrodes for every measurement. And basically, in the next cycle, we then rotate to the next emitting pair, 2 and 3, and we perform that whole measurement cycle all over again. Here, we're using adjacent electrodes. This technique is known as adjacent drive, and that's that's the sort of most common technique, although there's other kind of electrode excitation patterns that can be used. Now, four-pole scheme, big advantage is that it is actually resilient to contact conditions. So if the impedance changes while the user is using the system or whatever, it's not going to cause the output to differ that much. And that makes it more suitable for the wristwatch form factor when people are putting on and taking off the watch constantly. So in addition to the sensing mode, we can also adjust the number of electrodes. Tomo used 8 electrodes, as you can see here, the sensing paths shown. Well, if we go up to 16 electrodes, we will increase the number of sensing pairs and therefore the resolution. But the big trade-off is that we're going to have to spend longer doing all the measurements. Taken to a sort of an extreme in our case, we can go up to 32 electrodes. You see there's a lot of sensing pairs and also correspondingly a much, much higher resolution. So with this kind of setup, we can get a very high resolution picture of the internals of the arm. But again, the trade-off is that the number of measurements increases as the square of the electrode count. So Tomo1 could only obtain around 250 measurements per second, and that made 16 and 32 electrode configurations very slow. As you can see from the bottom row, the frame rate would drop to 0.6 frames, which is just not fast enough for interactive uses. So in order to perform our new explorations for our current implementation, we had to implement new hardware to sense faster and implement the four-pole sensing mode. This is just a schematic diagram, or the picture rather, of the sensing boards that we built. Schematically, our system works by multiplexing those electrodes. This allows us to rapidly switch between the electrodes. And compared with Tomo, we optimized the switching time, the ADC read speeds, the microcontroller software, and the sampling methodology to all significantly improve the speed of the measurement system. Details on how we actually achieved that are in the paper. When we could previously obtain 250 measurements per second with Tomo, the new system approaches 3,000 measurements per second. And that allows us to experiment with up to 32 electrodes, granting a significant boost in resolution. So here's a picture of our new prototype. It has 32 stainless steel electrodes, and we turn on a subset of electrodes whenever we want to test with 8 or 16 electrode configurations. This whole thing is actually completely wireless, battery powered. It costs about $100 US for our prototype, and of course that would come down significantly with commercialization. And it's much smaller and cheaper than medical systems, and yet it's still quite capable. The last sort of factor to tweak is the image reconstruction algorithm. Now, this is very important, actually picking the right algorithm to solve this EIT problem. In Tomo, we used linear back projection, and that's very simple, quite simple to implement, but actually very inaccurate. Doesn't model the problem very well. The second and most accurate approach is to use what's called a Gauss-Newton image reconstruction. It's an iterative process where every step you basically approximate an image and get closer and closer to what the image really should be, minimizing the error basically between the simulated measurements from your reconstructed image and the actual measurements that came out. Now, the problem is that's a really slow process. Doing all those iterations takes a lot of time, and it would take hundreds of milliseconds to run for our current system. So instead, we opted for what's called a single-step maximum a posteriori reconstructor, which achieves real-time reconstruction in a single step, and that lets us reconstruct images as fast as they come in. Again, details on the exact algorithms are in the paper. So we ran a couple of experiments to see sort of what combinations of factors, what combinations of electrodes, sensing modality, et cetera, were sort of optimal. We did an image reconstruction study and a user study for gesture accuracy. To test image reconstruction, we built a saline water tank, as you can see on the left, and dropped objects of known size and shape into that tank. This is a common evaluation strategy with all tomographic systems. These objects here are called phantoms, and you test basically computed tomography, MRIs, all sorts of stuff can be tested with this kind of setup. In the subsequent images, you'll see that red represents areas of high impedance. For example, here the plastic objects are high impedance, and blue indicates lower. So let me show you the results real quick. First of all, we have objects of different sizes. We used basically 3 different sizes, 1.5-inch diameter, 2.25-inch, and 3-inch diameters. You can see at 2-pole, we can sort of, we barely even separate the objects, let alone actually be able to tell that they're different sizes. But for 4-pole sensing, you can clearly separate those objects, and at 32 electrodes, you can even tell that they're different sizes very, very, very clearly in the output. We can also try with different numbers of objects. We have 1, 2, 3, 4, and 5 different numbers of objects, all of the same size. 2-pole sensing, you can sort of barely tell that there's 4 objects, in the 32 case, but it's also not very clear. But of course, there's a big difference when you go to 4-pole, and especially at 32, all of the objects show up, clear as day. And finally, the most challenging condition is to do different shapes. Distinguishing these different shapes the differences between these are very, very minute, not like different sizes or numbers of objects. Left again, we've got basically squares, triangles, circles, and rectangles. In a 2-pole sensing mode, you sort of barely register that they're there, and you can't really see the difference between them. At 32, you can see the difference. And the interesting thing about 32 here is you can see that the objects are different, but they're all very blurry. And the reason for that is electrical paths aren't actually like rays of light. They're not like penetrating radiation. They don't take straight line paths inside objects. They basically take the path of least resistance. And this is called the soft field effect. It means that basically we can't reconstruct exactly around very, very sharp boundaries because electricity simply doesn't work that way. So instead, we have to sort of do the best we can with the resolution that we have. This gives you a little bit of blurring. But even so, you can see that the triangle is very distinguishable from the other examples, for example. Okay, we also then tested image reconstruction in real time. You can see the results here. When you have 8 electrodes, the reconstruction is pretty crude. Now, I'll note that I've sped this video up to 4 times just so you don't have to sit through 2 minutes of this. At 16 electrodes, you can see we're definitely getting better here. And finally, we have 32 electrodes. See, moving the object around. We also, as finally sort of a more realistic test of the system, wanted to test out the armband on a biological sample with a known cross-section. Now, nobody at our school wanted to actually lend us a cross-sectional cut of their own arm, so we used a lamb shoulder instead. You can see how that lamb chop gets reconstructed by various configurations. In the 4-pole 32 electrode case, the bone and fat are clearly visible in that reconstruction. And bone and dry fat have a significantly higher impedance than muscle, which you can also see here. Don't worry, I won't show you this picture again. So, let me show you basically the gesture accuracy results. We recruited 10 participants, and we had them perform 11 different gestures split into 2 logical gesture sets, with 2 gestures, index, pinch, and neutral, shared between those 2 gesture sets. These are the same gesture sets that we used in Tomo, and in turn, those were taken from earlier literature. For each gesture, we collected 6 different measurement conditions and 10 different trials per condition. We ran 5 rounds of data collection, where the user was allowed to relax between rounds, for a total of 3,300 measurements over the 30-minute study. Like Tomo, we used machine learning to implement gesture recognition. But since we now have a fairly fast and accurate image reconstruction algorithm, we opted to use the reconstructed image pixels themselves for machine learning, rather as features, rather than using the raw electrode measurements as we did in Tomo. We evaluated accuracy per user as if the system was calibrated to each user individually. And for each user, then we performed a cross-round evaluation by training on 4 rounds of data and testing on the 5th, all combinations. Unlike a pure cross-fold evaluation, this approach ensures that our testing set doesn't contain data points that are temporally adjacent to those in the training set. So this basically temporally separates that, and that ensures that we don't accidentally accept overfit machine learning classifiers. Our results indicate that 4-pole sensing is a lot better than 2-pole sensing, and further, that increasing the number of electrodes basically monotonically increases accuracy. If you focus clearly on the most challenging condition, our combined hand-pinch gesture set, which has 11 gestures in all, you can see basically that we cap out around 84% for 2-pole, but for 4-pole, we sort of keep going up until around 94.3% at the 32 electrode case. Okay, so now to just wrap up, there's a lot of future work we'd like to do on the system. I think we've done some very great explorations over the last year, but there's more yet to do. As you can see, our accuracies sort of keep going up as we go from 8 to 16 to 32, and so we sort of want to know where that plateau actually is. We'd like to explore with more electrodes, 48 and even 64. As you know, this is going to require actually even faster sampling and even faster sensing. And furthermore, there's definitely a trade-off. As you increase the number of electrodes, each individual electrode gets smaller and smaller, and so the sensitivity will decrease. At some point, we will plateau, and we'd like to explore sort of where that is. We'd also eventually like to do continuous gestures using regression in human kinematics, and maybe eventually extend this to sensing the user's entire hand pose. And finally, we'd like to use EIT to not only sense gestures, but also sense biofactors, like, for example, bone density, fat distribution, pulse rate, et cetera, for even smarter wearables. Okay, thank you. I'll take questions.
If you raise your hand to ask a question, then the student volunteers will bring you the microphone. Questions, you know you want to. Yeah, perfect.
Hi, Robert.
Yeah.
Great work, thank you. Maybe can you just very briefly comment on the difference to EMG-based sensing?
Yeah, so EMG-based sensing is based on sensing basically the actuation of the muscles, whereas this is based on sensing basically the structure of the muscles. They're very similar, I think, in sort of high-level goals, but the idea here is that you can sense sort of more than just the muscles, right? You can sense factors beyond that, and those can tell you things that EMG sensing might not directly be able to tell you.
So do you think you could get more fine-grained information about the finger movement?
Yes, for example, when we move our fingers very, very slightly, we can actually see differences in the reconstructed image, and that's why we'd like to sort of explore to see if we can actually do things like hand pose. We think that's possible with something like EIT, where it might not be possible with EMG. Yeah.
Mm-hmm. And then maybe, I haven't read that part of the paper, but I would assume that the map inference algorithm has to have some prior assumptions about conductivity distribution. Is this like different for each user, or where does it come from?
The prior for MAP is not the conductivity distribution, but rather the finite element mesh and the electrodes themselves. So the positioning of the electrodes and that mesh that you generate. Basically, you need to know the rough shape of the user's hand, but you don't need to know the interior conductivity distribution. That's actually solved for by MAP.
Other questions? I have a question, which is, if you wanted to use this technique to interpret gestures on other parts of the body, so not with the hand and the arm, would there be any modifications or changes that you would have to make to the sensing device?
We'd have to make it larger, but I think that actually would be about it. Actually, you could definitely wrap this around a leg. You could wrap this around, torso, around the neck even. We think that you could basically put this around almost any part of the body and be able to infer basically muscle groups and other sort of organs attached to that area. So yeah, it should be generally applicable. But you would, for example, not be able to tell what the leg was doing from an armband, so you would need to move it.
Of course. Great. We have time, sure, for one more question. While we're doing the last question, could the second speaker come set up their laptop?
Hi. Right. Great work. And I'm just wondering, does it have to go around, around the full arm, or can it be partial?
It can actually be partial, yeah. It can be partial, and in fact, that's a very interesting use case for us. Now, for us, for an armband was just convenient to make it all the way around, but you can put EIT sensors, rather, electrodes on the forehead and actually sense what the face is doing. For example, potentially.
Yeah, definitely.
Something we'd like to explore.
Yeah. Okay, great. Thank you.
Thanks. Let's thank our speaker again.